declining bias direction, in the forward bias direction compared to the negative bias direction, which is just a characteristic of a PN diode. We can also use this to create a CMOS inverter structure. Now, CMOS, by definition, it's complementary MOS, so you need N and P. And so here we have an n-FET and a p-FET. When we connect the circuit with this arrangement, our backgate becomes our input voltage. Our Vout is measured across these two contacts. We see this inverter structure, which basically is just changing the polarity of your input voltage. So here we have a negative input voltage, which becomes a positive output voltage. Now, this device really is just a proof of concept because it's sitting on a layer of silicon dioxide, which is very thick. And that's why this region here, this region between the on and the off state, is very wide. It's just related to that insulator thickness. And we're currently developing devices with a local graphene backgate, which will increase, basically increase the gain of this inverter structure. But there are several, I think, key points with this device. One is that it's using a single material. That's very, very useful for the fabrication process. The other is that we've used a one-step metal deposition. We're not depositing different metals or using different processes to integrate our metals, or metal contacts. And the other is that it's just a one-step exposure process. So those are all ways that we've simplified the fabrication process to create these very useful CMOS inverter structures. Now, having introduced to you the fact that we can do N and P type operations with WSC2, the next part I want to focus on is improving the P type performance of these two-dimensional transistors. And that's one of the current challenges in this field. And there are two ways in which you can do that, two different and quite promising ways. One is the oxidation technique, which I described previously to you, either using oxygen plasma or ozone. Both are okay. You just transform the entire surface of your WSC2 to this tungsten oxide. And the other is the way in which you integrate the contacts, using what we call via contacts or van der Waals contacts or transferred contacts. You will see all these names in the literature. And basically what you do is you take your 2D material HBN, 2D insulator, you etch some holes in it, you deposit the metal in the holes, and then you pick up that layer which has your contacts embedded in the HBN, transfer it onto your 2D material, and then make a sandwich structure. So given that both of these methods are very good at improving P-type characteristics in these devices, we'd like to get the best of both worlds and combine the two. Now, remember that I told you if you oxidize the entire surface of your tungsten diselenide, then you get a strong P-type doping. So this shows this shows a control device, which is just WSC2 on silicon. The intrinsic properties are this red line here, so you have ambipolar behavior on a slight N and P, or current in the N and P regions. And then if you oxidize it, you basically get a strong, a large current which doesn't switch off within your measurement range, which isn't very useful to anybody. So although it's heavily p-doped, you can't use this to do any FET type operations. Now there's a solution, and that is just to wait. But the problem with that, or two problems really, is one is how long do you wait, and two is what environment do you leave it in it, because it depends if you leave it in ambient, just in the air around you, or if you leave it in an inert atmosphere like nitrogen, or whether you leave it in a vacuum. That will change this threshold, where this threshold voltage ends up. Here, we just left the sample for a day in atmosphere and remeasured it, and you can see that, yes, it does turn off within our measurement range, but the current has dropped significantly, This isn't a very pretty p-type FET, so this isn't particularly useful to us. And so the solution that we propose to this problem is to integrate these transferred via contacts with holes, etched holes next to the contacts through which we can expose the sample to this oxygen plasma to create basically a metal and then strongly doped P semiconductor intrinsic channel with strongly doped P and then your metal again. And if you do that, if you have this, if you have a metal strongly doped next to a strongly doped semiconductor, you reduce the barrier width, and it's very easy for electrons to get into that semiconductor, and it reduces your contact resistance significantly. So the fabrication of these devices, we have 3 layers. Here, this is our top layer in which we've etched our holes, and we've also deposited our metal contacts. And you can see there are little holes next to the contacts there, or little dark spots. There are etched holes. The fabrication process here, from the side-on view, it is here we etch the holes, deposit the metal contacts, and then transfer that layer onto our middle layer, which is our tungsten diselenide. Pick up both of those and stack them on our bottom boron nitride layer to create this sandwich structure. Finally, we just etch a rectangle so that we remove all this unwanted material around the edge. There are some very, very key advantages of this approach. One is that we've got very precise controlling over the size of our dopant region. We can control its location very well, because this is just patterned by E-beam lithography. We can control the doping levels by changing the length of time that we oxidize this sample. And we also, importantly, protect the channel by using this pickup method, so that your channel isn't exposed to any contamination during further fabrication processes. And so really, in the following measurements that I'll show you, think of these etched regions as extensions of your contact, or you could call them degenerately doped contacts. So it's a strongly doped semiconductor next to contact. So you'll be pleased to know that we do actually achieve what we set out to do with these devices. The red trace here shows the pristine state, so before exposing this sample to an oxygen plasma, we have ambipolar behavior, but actually much stronger n-type characteristics. Once we just need 60 seconds exposure to a low power oxygen plasma to see this very nice p-type behavior. What I mean is that we have a large on current, we have a steep turnoff, and we also have a threshold voltage which is very near to 0. So it's well within our measurement range. One crucial question is how repeatable this process is. And if we compare similar geometry contacts on the same device, we see remarkably similar transfer characteristics. So pinch-off voltage are basically exactly the same voltage, and very, very similar on currents. So that's very pleasing. Now, in terms of reproducibility, we then look at making another device, again, very similar. So here, just focus on the black and the green trace. They compare sample A and sample B. It's the same geometry, same length channels in both samples. We see very similar on currents. We see a pinch-off voltage, basically both close to 0, and both have a very sharp turn on. Now, for comparison, we also measure a control device, which is just tungsten diselenide on a silicon dioxide wafer. So we oxidize that sample, leave it for a day, and then come back and measure it so it does turn off within our measurement range. And we find that the current has dropped, and we have a much shallower turn on. So none of those are particularly ideal. So this is just demonstrating, again, the I guess, the power of our device. Now, interestingly,